There's only one planet that we're certain has life, and that's our home, Earth. Since at least the era of classical antiquity, over 2 millennia ago, humans have pondered the possibility of life on other worlds. The famed Greek philosophers Democritus and Epicurus, who held that everything was composed of infinite atoms in an infinite void, believed there must be other similar worlds out there. According to Epicurus's disciple, Metrodorus of Chios, if our world was the only one, it would be like a single ear of wheat growing on a vast plain. Of course, this was long before the invention of the telescope, making the idea quite abstract for the time. It came at a time when the dominant view was still geocentric, putting the Earth at the center of the universe. Now, we're closer to finding extraterrestrial life than ever before. The international search effort has been well underway since the 1980s, utilizing a plethora of advanced tools, from radio telescopes to infrared instruments on satellites. We have currently over 5,500 confirmed discoveries of exoplanets. Most of these were discovered by the Kepler Space Telescope and are all compiled in NASA's Exoplanet archive. Once cataloged, they are assessed for habitability, and if there's potential, they're added to the Habitable Exoplanets catalog. This work is carried out primarily by the Planetary Habitability Laboratory at the University of Puerto Rico in Arecibo. What they look for first is if the exoplanet has the conditions needed for liquid water on the surface. The range around a star where planetary orbits are ideal for liquid water is called the habitable zone, or the Goldilocks zone. This is thought of as the most important requirement, since on Earth, where there is water, there is life. It's assumed that if a world can support liquid water, life won't be too far away. There are numerous other factors that need accounting for, however, such as radiation from the host star and atmospheric composition, alongside various geophysical factors. All exoplanets on the catalog are assigned an Earth Similarity Index, or ESI. This number ranges from 0 to 1, with 0 meaning no similarities and 1 being identical. The rationale for this is that Earth is the only place we know life exists. Thus, researchers think that the closer an exoplanet is to our home, the stronger the chance of life. Not all astronomers are in agreement on this, however, and in the past decade, some have argued that the assumption is misguided. While Earth is indeed a hotspot for life, we can't be certain that it is the most ideal home for life. It's often said by astronomers that the more you learn about Earth, the more you realize just how lucky we are to be here. It's not just liquid water that makes our planet a paradise. There are also an abundance of other factors. For example, the magnetic field that absorbs most of the sun's harmful ultraviolet radiation, or the tectonic plates that form continents and bring heat to the surface. We also can't forget Jupiter, whose gravity may capture asteroids and comets hazardous to life. So there are good reasons to describe our home as perfect for life. However, in 2014, physics professor John Armstrong and astrophysicist Renee Heller challenged this claim. They proposed that certain kinds of planets with characteristics very different to Earth could be even more habitable. In fact, could be what they call superhabitable. They define superhabitable as a planet that can sustain a more diverse selection of plants and animals. The researchers still assume that life needs water, but believe that there could be planets better optimized than Earth for biodiversity. They reject the idea that the Goldilocks zone is a good indicator of habitability. A lot of rocky worlds in habitable zones aren't habitable, and geothermal processes can make planets outside of the zone habitable. One such example is Jupiter's icy moon Europa. While its surface is covered in ice, scientists believe that a subsurface ocean is hiding below, kept warm by tidal heating. According to Heller and Armstrong, the search for extraterrestrial life should be less human-centric and more biocentric. Primary criteria should include a planet's age, mass, location in its system, host star's spectral type, and a few other features. The concept isn't limited to just exoplanets, but also includes exomoons. Superhabitable planets, the researchers suggest, are likely slightly larger, more massive, and older than Earth. A larger surface area would allow for more shallow seas, which warm more easily than deep oceans, making them comfortable habitats. In terms of mass, the ideal would be roughly twice Earth's, optimal for plate tectonics, a strong magnetic field, and a thick atmosphere. Created by the rotation of a liquid outer core, Earth's magnetic field shields us from cosmic radiation. Theoretically, a more massive world could have a stronger magnetosphere. A thicker atmosphere would make the surface warmer, and historically, warmer epochs on Earth have encouraged biological diversity. Ideally, a superhabitable planet should orbit a different kind of star to the Sun. The Sun is a yellow dwarf, but orange dwarfs, which have lower luminosities and are less massive, have significantly longer lifespans. Called K-type main sequence stars, orange dwarfs remain stable for 17 to 70 billion years, far longer than our Sun's 10 billion year shelf life. This would allow more time for life to originate and evolve. As a bonus, they emit much less UV radiation too. Currently, there are 24 exoplanets deemed potentially superhabitable, although only 2 of these are validated planets. However, it's thought that there might also be other contenders already cataloged and overlooked. This leads us to ask the exciting question, what would life be like on such a planet? Of course, we can only speculate about the specifics, but rainfall would likely be more common, and native flora very different. With a denser atmosphere and higher mass, life might be larger and more common. Plants might follow different processes of photosynthesis due to the different spectral output of other host stars. Orange dwarfs are cooler and redder than the Sun, and plants might evolve pigments optimized to absorb those wavelengths. Their leaves might be blue or some other color rather than green. If we managed to discover a superhabitable planet, it would have major implications. For one thing, it could provide invaluable insight into the hypothetical Great Filter. This is the theory that life is rare in the universe because there's some unknown barrier between the earliest stages and the highest levels of development. Perhaps, for example, life tends to destroy itself. Or the universe, with its asteroids and rogue black holes, is far more dangerous than we think. We're currently unsure whether such a great filter exists at all, and whether it's behind or ahead of us. Life on a superhabitable world could shed some light on this topic. If we find that life tends to get stuck in its simplest form, that barrier might be behind us. If, on the other hand, we find a planet teeming with complex life, having comfortably survived for billions of years, well, maybe we should figure out how they did it. Perhaps they had no desire to leave their homeworld and avoided some risk of collapse inherent in interplanetary expansion. Alternatively, we might find the ruins of a once great extraterrestrial civilization, which could also suggest some answers. Both scenarios would put the barrier ahead of us and give us some idea of what to watch out for.